Your new AI application looks incredible. The demo is flawless, but in production, it's failing in one of two ways. First, you ask it to generate code or an API call, and it just quietly breaks downstream because it's not functionally correct. The second, more sinister failure is when you ask it for a summary or an answer, and it gives you something that looks right, but completely misses the meaning, like the difference between let's eat grandma and let's eat grandma. Relying on vibe checks to catch these is a recipe for disaster. To solve the first failure, we need our first pillar of objective evaluation, functional correctness. The principle is simple. We don't care what the AI's output looks like. We only care if it works. For tasks like code generation, SQL queries, or API calls, this is the gold standard. We evaluate the AI's output by running it against a set of predefined unit tests. If it passes, it's correct. If it fails, it's wrong. There's no ambiguity. This is often measured with a metric called pass at K, which asks, if we let the model generate K different attempts, does at least one of them pass all the tests? It's a pragmatic approach that mirrors how developers actually work. All right, let's make this real with a pre-built script. We're going to evaluate an AI's ability to write a function that finds the greatest common denominator. First, you can see we've defined the AI's correct attempt. Next, we have a version with a subtle but critical off by one error. Our evaluation harness is a list of test cases, simple inputs, and their expected outputs. Now we run our evaluator. Watch the output. For the correct function, our script confirms it would pass all test cases. But when we test the buggy function, it immediately flags that the tests would fail. The final summary is crystal clear. One function passes, the other fails. This is the power of functional correctness. It's a definitive, unambiguous signal that catches bugs before they hit production. Functional correctness is powerful, but what happens when the task is summarization or answering a question? There's no code to execute. You might think, I'll just check if the model's answer exactly matches my reference answer. But that's incredibly brittle. If your reference answer is the sky is blue, and the model says the color of the sky is blue, an exact match test fails, even though the meaning is identical. Worse, lexical similarity, just matching words, can be catastrophic. The sentences "let's eat grandma" and "let's eat grandma" share most of their words, but their meanings are worlds apart. We need a way to measure meaning, not just words. This brings us to our second pillar, semantic similarity. The core idea is to convert text into a meaningful numerical representation called an embedding. Think of it like giving every sentence a coordinate in a high-dimensional meaning space. Sentences with similar meanings, like "how are you" and "how's it going," will be located very close to each other in this space, even if they don't share words. Sentences with different meanings, like "the cat sat on the mat" and "AI research is fun," will be far apart. Once we have these embedding vectors, we can measure the distance, or more commonly, the angle between them, using a metric called cosine similarity. A score of 1 means they are identical in meaning, while a score near 0 means they are unrelated. Now let's see how we can measure meaning with code. In this script, our goal is to see if an AI's answer is semantically close to a reference answer. Our reference is the weather will be sunny and warm tomorrow. We have 2 candidates. Candidate 1 is expect clear skies and high temperatures. Different words, same meaning. Candidate 2 is the stock market experienced volatility today. Totally different topic. Now, we'll run our script, which under the hood uses a sentence transformer model to turn these sentences into numbers and compare them. Look at the simulated output. Candidate 1 has a very high similarity score of 0.92, while candidate 2 has a very low score of 0.08. The analysis is clear. The AI model can understand that clear skies and high temperatures mean the same thing as sunny and warm, which is something a simple keyword match would completely miss. So you now have 2 powerful tools, but the most important skill is knowing when to use each one. Here's a simple decision framework. Start by asking, is my AI's output executable or verifiable against a single right answer? If the answer is yes, if it's generating code, SQL, JSON, or a specific value, then your choice is clear. Use functional correctness. It's objective and definitive. If the answer is no, if the output's meaning must match a ground truth, but the wording can vary, like in summarization, question answering, or paraphrasing, then you need semantic similarity. This framework is the foundation of a robust evaluation pipeline and will save you from using the wrong tool for the job. So there you have it, the 2 pillars of objective AI evaluation. Functional correctness for when things must work, and semantic similarity for when they must mean the right thing. These aren't just theories. They are the practical tools you'll use every day to build reliable, trustworthy AI systems. If this tutorial helped you build your evaluation toolkit, hit that subscribe button because you've now mastered objective tasks. But what about the hard stuff? How do you evaluate creativity, style, or helpfulness? In the next video, we're tackling the most powerful and dangerous evaluation method, building an AI judge from scratch. You won't want to miss it.